Welcome to Ready to Derive. In this video, we're going to learn about L'Hopital's rule. Actually, I need to just correct that. There should be that little symbol above the O to get the pronunciation of L'Hopital. Because I don't know how to do that on the computer, later in the video, I'll be using an S in there instead. So you'll see it written slightly differently. L'Hopital's rule is a way to, a very helpful, powerful way to find limits. But you may be wondering why this is happening in a unit on derivatives. And that's because L'Hopital's rule actually uses derivatives to find the limit, as opposed to the reverse. So if we recall the definition of a derivative, it was expressed in terms of a limit. So without, we needed limits first. So we needed a limit to define a derivative, and we have only gone in this direction. With L'Hopital's rule, we're now going to be able to, using the tool of derivatives, evaluate certain limits, which would otherwise be very hard to evaluate and would require sort of more advanced techniques. So in this video, you'll learn about indeterminate form, and you'll learn about the many different ways in which L'Hopital's rule can be used. So let's get started. So let's start with a couple of warm-up limits, ones that we've met before. So this limit as x goes to 3, if we plug 3 in there, we get 0 over 5 equals 0. That's pretty straightforward. We can handle 0 in that scenario. If we plug in 3 here, we get 5. So plug in 3 here, we get 5 over 0. And luckily, whether x is approaching 3 from the left or right, because that factor is squared, we'll get 0 in the positive sense. So we can even handle 5 divided by 0 in the positive sense. That will be infinity. So that's indicative of a vertical asymptote at x equals 3 for this function. But where we run into trouble is when we have something like this, and we plug in 3. We get 0 on the numerator, and if you plug in 3 in the denominator, you get 0 also. And 0 over 0 is known as an indeterminate, and it's indeterminate because if you think about it, you could make it whatever you think you would like. So we could say maybe that's equal to 5, because you know what? 5 times 0 to check if it works. 5 times 0 is 0, that works. Or maybe it's 100. Because we know that 0 equals 100 times 0. So the answer is indeterminate. And we have used algebraic methods to solve problems like this, and we will do that in the next slide. But L'Hopital's rule is going to help us to tackle problems that generate 0 over 0 as an example of an indeterminate form. And other indeterminate forms is infinity over infinity, 0 times infinity, because who wins? So, if you take infinity times 3, 3 times infinity just gives infinity. If you do 3 times 0, it gives 0. So who wins the fight if it's 0 times infinity? And that will, again, L'Hopital's rule will help us to answer that. 1 to the power of infinity, 0 to the power of 0. So 0 cubed is 0, but what is 0 to the power of 0? Indeterminate. And infinity to the 0th power. And there's one more indeterminate form that's kind of common. You get a limit of a difference of two functions, and it works out it's infinity minus infinity. Is that answer 0? Probably not, because there's different magnitudes of infinity. But I kind of, this one, if you can just bring the two fractions to a single fraction, get a common denominator, etc., you're really reduced to one of these two forms. So that one is not as interesting to me. But in the next slide, we'll get to see an example of L'Hopital's rule in action. So let's consider that third limit we were looking at in the previous slide, and we'll actually just look at the function. If I graph that function using Desmos, I see that it has a vertical asymptote at x equals 0 along the y-axis, but it's always good to check the domain because other issues might not appear if you don't look carefully. So recall that we would do that by factoring the denominator. X minus 3, x minus 3, and you might be tempted to cancel those x minus 3's right now, but first of all, we should say we can see that in the domain x is not allowed to equal to 0, and x is not allowed to equal to 3. Now, that's interesting, because if 3 cancels out, how does that show up on the graph? Well, what detail we're missing on the graph, I'll add it right now, is that there's actually a hole at x equals 3. So the problem with 3 is that it causes, remember from the slide before, if you plug x equals 3 in, it causes 0 over 0, which is indeterminate, which indicates the presence of a hole. And so why would be interested in this limit? Well, that limit will actually give us the coordinate, the y coordinate of the hole. So we see the y coordinates, it's some fraction less than 1. So at x equals 3, we've got a hole, and we need to find the y coordinate, and that's why we'd want to answer a limit statement, like a limit problem like this. Now we see from above that the x minus 3 is cancelled, so you're really left with the limit as x goes to 3 of what, so we have a 1 here, the x minus 3 is cancelled, so we just get left with 1 over x, which we can use direct substitution and say that that's 1 over 3. So we have found the y coordinate to be 1/3. So what I'm going to do next is actually show you L'Hopital's rule in action without kind of explaining all the details and the preconditions, because it's really kind of neat to see. So this is what L'Hopital's rule allows us to do. Under certain conditions, which we'll see in the next slide, if you take the derivative of the numerator and the derivative of the denominator of the function, so the derivative of the numerator is 1, and the denominator is 2x minus 3. We are at a place, well, this is what L'Hopital's rule allows us to do. We're at a place where we can use direct substitution, and we can plug in 3, 2 times 3 minus 3, and we get 1/3 the same answer as up here. So sometimes it's nice to see something like L'Hopital's rule in action before you get sort of bogged down with all the necessary conditions. So L'Hopital's rule. So suppose that f and g are differentiable functions, and there's that restriction on g prime I'll explain in a moment. There's two scenarios. So either the limits of f and g are both 0 as x approaches a, or they are both positive or negative infinity. And what L'Hopital's rule says is that the limit of the quotient of the two functions will equal the limit of the quotient of their derivatives. So in this case, when f over g would be, that's the 0 over 0 indeterminate case. And this is the infinity over infinity. Notice you can have, it can be plus or minus that version. So in those two scenarios, you can apply L'Hopital's rule if the limit on the right side exists, of course. And this condition about g prime x not equal to 0 near a is, if we think about limits, sometimes the function doesn't exist at x equals a, but the limit exists. But when you consider the limit from the left and the right, if g prime of x was equal to 0 to the left or right of a, that would be very problematic in this function. It would blow up the function, so that's not allowed. So we are not going to derive L'Hopital's rule because it would make this video interminably long. Instead, we're going to get straight into some practice. So for our first practice problem, we actually proved this result using the squeeze theorem in Unit 1. So, but because we use it so rarely, probably can't even remember the answer to this limit. So now we're going to use L'Hopital's rule to save us having to even memorize this. So the first thing we need to do is to check that it's either 0 over 0 or infinity over infinity. So if we put 0 into the numerator, 1 minus cosine of 0, well, cosine of 0 is 1, so that would be 0. And obviously if we put 0 into the denominator, it would also be 0. So we have the type 0 over 0, which means we can use L'Hopital's rule. So let's take the derivative of the numerator. The derivative of 1 is 0. Negative cosine will actually get us back to sine. And the derivative of x is just 1. And we are at a stage where we can just substitute in because we have the sine of 0 over 1, which is 0 over 1, which is just 0. And so maybe that one rings a bell, or this next one. We did know what from the squeeze theorem again, the limit as x goes to 0 of sine of x over x. We at one time had that memorized, but we might not now. So let's just do our check. So sine, so the type, I like to sort of list the type here. So sine of 5x, sine of 0 is 0, 2 times 0 is 0. So that's the indeterminate type we have. We can use L'Hopital's rule. So let's take the derivative of the numerator, which would be 5 cosine 5x, over the derivative of the denominator, which is 2. And we're at a stage where we can do direct substitution. So cosine of 5 times 0, which is 0. And so the answer is 5/2. All right, the next one, we've seen limits like this before as well. And we had ways of figuring this out algebraically, or if you recall from pre-calculus, ways of remembering when we want x to go to infinity, we're looking for a horizontal asymptote. But let's just plug in. So we'll plug in, when we say plug in infinity, we're thinking, so 5 minus 2 times infinity, that's going to be a very large negative number. So that's going to be negative infinity. And 3 times infinity, huge. Infinity plus 4, huge, just infinity. So this is our type. It's negative infinity over infinity, which is fine by L'Hopital's rule. So we can apply so that the conditions are met. So we need to take the derivative of the numerator, which would give us negative 2 over the derivative of the denominator, which is 3. So, we don't even have to plug in negative 2/3. And if you recall, that was the coefficient of the leading terms was the way we used to do that in pre-calculus. So finally, we have the limit as x goes to pi over 2, 1 minus sine x over cosecant x. If we plug in 1 minus sine pi over 2, we get 1 minus 1, which is 0. But if we do this here, so 1 over sine, cosecant is 1 over sine, we actually get 1 over 1. And because the conditions aren't met, we cannot apply L'Hopital's rule. So be careful, because it doesn't always apply all the time. You have to either have 0 over 0 or infinity over infinity, at least for now. So now we're going to try a problem where we get to use L'Hopital's rule a couple of times. You can use it many times in a row as long as the conditions are met at every step. So the proper formatting refers to what you should really do when you're establishing whether you have 0 over 0 or infinity over infinity is to take the numerator and denominator functions and look at them separately. So if you had to show your work or justify your work, you would want to make 2 separate limit statements. So we would first of all, the limit of the numerator, we are allowed to plug in x equals 0. E to the 0 is 1 minus 1. The answer is 0. And we would repeat for the denominator, function in the denominator. And that's pretty easy to do. 0 squared equals 0. So once we've established that we have, indeterminate form 0 over 0, we can use L'Hopital's rule. And so we can take the derivative of the numerator and the denominator. So that's e to the x. The derivative of minus 1 is 0, and minus x is this. And the derivative of x squared is 2x. So that allowed us to move from here to here, and let's put an H for L'Hopital's rule. Now, if I plug 0 into the numerator and denominator again, I think I'm going to get 0 over 0. So let's look at it one more time. So now let's take e to the x minus 1, and that's e to the 0 minus 1. 1 minus 1 is 0. And the denominator function, 2 times 0, also 0. So we have another indeterminate form of 0 over 0. And so we can apply L'Hopital's rule another time. So we get limit as x goes to 0 of the minus 1 goes. And fortunately, the x goes in the denominator, which allows us to just substitute in 0 and for x, and we get 1/2 as the answer. So let's look at a limit that will generate this type of indeterminate form, infinity times 0 or 0 times infinity. So if we imagine trying to plug x as infinity in here, we would get infinity cubed, which is just a very big number, infinity times now e to the negative infinity squared. So if you recall the graph of e to the x, it looks like this. or any exponential graph. So if you head to negative infinity, raise e to the negative infinity, you're basically heading to 0. So we are sort of got this situation going on. But this is really a familiar indeterminate form in disguise. So what we were going to do is just rewrite this as x cubed over e to the x squared. And we're also going to dispense with like the formal notation. We're just going to go back to our method of checking what type we have. We just use arrows. So if we plug infinity in for x, x cubed is going to go to infinity. And if we plug it into e to the x squared, no negative now. So e to a very big number. So as x goes to infinity in that direction, e to the infinity is going to be huge. And look where we are. We're at infinity over infinity. So we have the indeterminate form that we need to apply L'Hopital's rule. So let's indicate that with an h again. So let's take the derivatives. So infinity, so we get 3x squared over, we have to use the chain rule. So it's e to the x squared times the derivative of x squared, which is 2x. And let's just cancel that. So we have cancel the x's. So we have 3x over 2e to the x squared. And once again, if we put in infinity, 3 times infinity is huge. E to the infinity will also be infinity, and we can use L'Hopital's rule again. So let's take the derivative of 3x is 3. The derivative of 2e to the x squared, so we're going to get 4x e to the x squared now. And then so now we're at a situation where if we plug infinity in, well, the numerator is not going to be infinity anymore. But we're in a situation where everything on the bottom, so we can't use L'Hopital's rule again because we don't need to. Because if you're taking 3 and dividing it by, well, 4 times infinity, huge, e to the infinity, huge, you're really taking 3 and divide it by infinity. And therefore that is going to go to 0. So the limit as x goes to infinity of this expression equals 0. Or remember what we discussed earlier, even though that's going to infinity and that's going to 0, the question is who won out, who was more powerful, and clearly this term was more powerful than infinity, and the limit ended up being 0. So for our last practice problem, we're going to look at indeterminate form of the type 0 to the 0 power. So we haven't seen any of these types yet, but this method, this process that we're going to do for this practice problem can be used also to tackle problems of the form infinity to 0 or 1 to the infinity. In these 3 scenarios, L'Hopital's rule can be used. So let's have a look at this. So we can see that if we plug in x is 0, we get 0 to the 0. So check, we are indeed in that scenario. And we're going to do some kind of a clever manipulation to make this problem possible. So this first thing we need to acknowledge is that any quantity can be written as e. So any quantity b can be written as e to the ln b, because e and ln are inverse operations, and that would drop down b on the right hand side. So the first thing we are going to do is rewrite this as e to the ln x to the power of x. Now you don't know why we're doing this, but you will see as things unfold. So we are doing this, for example, this property of logs, where you have log of some number raised to a power, you can drop that down in front. And that gives us this. So e to the x ln x. And then another important property of limits, limit of a composition of functions. It says that if you want the limit of f of g of x, so this is, think of this is the outer function, the inner function. You can just bring that limit into the inside function. So you can evaluate f at that limit of g as long as this exists, right? So as long as that limit exists and as long as f is continuous at whatever that limit is. which in this case it will be. So I'm going to rewrite this. Basically, the outer limit is e. That would be the function f of x. So I can bring the limit statement by this reasoning into the inner function. And the inner function is just x, ln x. I'll put a little parentheses around it to keep it there. Now we're just going to examine this exponent a little more carefully. The limit, so the exponent of e that we need to work out is this. And now we're going to do another algebraic manipulation. We are going to rewrite this as ln x over 1 over x. So that is definitely a clever manipulation, because so dividing by 1 over x, dividing by a fraction is the same as multiplying by its reciprocal. So that gets you back to the same thing. And now let's do a little test. If we plug x is 0, if we approach 0 from the right, and ln of x, that will actually head to negative infinity. And don't forget that ln looks like this. So as we approach 0 from the right, ln is heading to negative infinity, and 1 over 0 approaching from the right will be positive infinity. So look at that, we have that indeterminate form from before. So we can just take the derivative. We can apply L'Hopital's rule. So we would get the limit as x goes to 0 plus, and now we take the derivative. The derivative of ln x is 1 over x. The derivative of 1 over x is negative 1 over x squared. If we just simplify, keep, change, flip, however you want to think about it, we would get negative x left, and we can plug in and we would get 0 as our answer. So that means this whole limit up here, this exponent we just discovered is 0, which allows us to say that this is e to the 0, which we then know is 1. So we found the answer to what looked like an impossible limit to calculate. And as I said, the same technique can be used when you have a power that looks at power of a power in that form or in this form. But for the sake of brevity, we'll stop there.
And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and or subscribe to my YouTube channel, Ready to Derive. Thank you.